Okay, we are come to design a patch antenna with resonating frequency 4.3 gigahertz, and I believe everyone knows how to calculate for the patch length and weight using the EM um, website and the feed line as given. So as you can see, my patch length is 17.94, weight is 23.13, all in millimeters, and the feed line is having the length to be 10.46 and weight 3.58, and my substrate is Rogers RO4003, and the dielectric constant is 3.55. The height of the substrate is 1.6 millimeters. So there are equations that you can use, but with the software it is so easy to come by. Okay, sure. So these are the parameters for my design. Let's go to software. Okay. First, so my first rectangle, I'm going to name it patch. Enter. And I come here, and I change the dimensions. My length. This 17.94. So with the positioning, I'll take the negative of the weight, which is the x-axis. Always remember your x-axis is the same as the weight. Don't forget. So okay, I'm giving the position for the height. The elevation is supposed to be 1.6 because the height of the substrate to be 1.6. So the patch is supposed to lie exactly on the surface of the substrate. So this is the reason why I did this. Sorry, I have to make this 2 so that it will be at the origin. Okay, so fit on. Okay, so let me change the orientation to top. Alright, and I use my pan. This. Okay, next I'm going to introduce my feed line. Sorry. Okay. So over here in other videos you realize the feed line is attached. For the sake of impedance matching, you are supposed to make sure the feed line overlap. This will take care of the impedance matching. So I'll name it feed. Then I come to this place. The dimension for this is 3.58. Then this is 10.46. the feed line too should have an elevation of what? Should have 1.6. It should also be at the same elevation as the patch. Okay, let me reduce this to something like say 8 or 9 or 8.5. Then make this one negative 1.7. Okay. Oh, this not good. This not good. So you could see with the positioning, I want the feed line to overlap the patch. So watch what I'm going to do. Because the y-axis is moving in this direction, the value I have at the positioning, I have to reduce it more. So I'm going to make it 4. Okay, 4 is okay. 4 is okay. Alright, so my next thing I'm going to do is to introduce the gap. So there's the thing that will take care of the impedance matching. Alright, with the gap, we take something small, shouldn't be too big. Okay, so you name it gap. Alright, over here you check whether it's at the same elevation. You leave the rest, it's okay. Okay, so watch closely. I want to produce another gap here, but I don't want to draw. I just want to use a mirror to project a different gap at the other side. So I'll select this, come to this, then I'll come to I see a triangle, then I move to I see a quadrant, then I click. Perfect. So this the mirror, this is the mirror of this. Alright, so fit on. Then the next thing I do is to merge, unite the feed line in the patch. So I've united. Perfect. And the second thing I do is to subtract the gaps. Subtract the gap. See something like this. Okay, that's subtracted. So fit. Alright, so I want to see it one. Alright. Okay, so I'm going to introduce the substrate. If I introduce the substrate, let me change the rotation. Okay, I think this is okay. This is okay. This is okay. Alright, so I'll change the name to substrates. I change the material to Rogers. Okay, so type Rogers. This expected, so it's 3.55 as you can see here. Take OK. So when I'm done, I come to create boss. Then the orientation, the position for the substrate is at ground 0, but the height is supposed to be 1.6. Because the patch can get enough of the substrate as I've drawn it. Okay, I leave it like that. What's this? No, the patch cannot get enough of the substrate, so I need to work on my dimension. Let me see. Okay, so I need to increase the X and the Y. So let me increase it a bit. make this, let make it 40. Let make this 36. Okay, so 36 divided by 2 is 18. 40 divided by 2 is 20. I think this should be okay. Okay, this is okay, but the y part is too big for me, frankly speaking, so let me reduce the y size to 32, 36, 34. Then let me make this, make this 17. Okay, this is cool. So let's check whether okay, this okay, this okay. So now I want to introduce my ground. Okay. Alright, so okay, this is the back of the patch. Let me introduce the ground. Alright. So our name is ground. So for the ground, we are at ground 0. Perfect. Alright, so I'm going to assign a citation. Sorry, yeah, kind of. I'm going to assign perfect electrical intensities to the patch and the ground. So I come here and right click, assign boundary, then perfect. Then for the ground. Okay, I've assigned to the ground. Let me assign to the patch. Perfectly. Okay. So I come to this place to check whether indeed it has been okay. Okay, perfect. I'll now come to introduce the pots. Alright. So with the pots, I change this to 8. Then I select this, control. Alright. Then I come to this place. You come to sweep. Okay. Alright. So our name is pots. Enter. So I want to work on pots. Okay. I don't want to see this. I want to see this. I want to see this. Okay, so I made a patch substrate and the ground invisible because I want to work on the pots. Yes, come to fit all. Then you assign an excitation. So you come to assign excitation. You come to pots, the modal pots, the modal lamp pots. Okay, whatever you see, leave it. You come to next. Then the line integration line, you choose to new line. Okay, So you move along the length until you see a triangle that indicates the midpoint of the pot. Then you move upwards, you see another triangle. Okay, after you should see defined under the integration line, that means you are good to go. Okay, finish. Alright, so okay, so the reason for making the parts substrate and the ground invisible is to have the magnanimous space to work on the pots alone. So after I'm done, I can come to show all objects in the active view. Select it, everything will come. Then okay, so over here I can give my parts a color. Yellow is cool. My ground, I'll give it yellow. Okay, so you can see it's cool. It's very, very cool. Alright, so first one. The next thing I'm going to do is to introduce a create open region. So it should be at radiation, and that's okay. So there's it. So within 20 minutes, you should be able to do all these things fast. So you come to radiation, you set far fade, then change this to 0, step size 10, change this to 360, the step size is also 10. Okay, then you come to analysis, you add an advanced analysis. So the frequency I'm supposed to get is supposed to be 4.3. The number of passes 25. Okay. Alright, so for this I can even start from 4 and end at 4.8. Then I change this to linear step. Come here, change it to 0.01. Fast preview. Okay, so my 4.3 over here. So I can even let it end on 4.6. Okay, so it's too much. 4.6. Okay. Alright, so it's in the middle. That is cool. It's very cool. Alright, so okay. After this, you come to validation check. Everything is perfect with no error. You close it, then you analyze everything. Oops, so because I didn't save it with a name, I need to give it a name. So I'm going to call it patch antenna. Patch antenna. Okay. So after I've saved it, the simulation can now start. Right, so the simulation is going on. And when it is correct, perfect, you should receive a message over here with no errors. Okay, so let's wait for the simulation to complete. Okay, so the simulation is complete. Alright, so you come to results, then you plot your graphs. Okay, the first plot is S parameter. So you are going to check, God I beg, let us cross negative 10 dB. Okay. Alright, so wow, this is so good. This is perfect. Very perfect. So you can see negative 10 dB and the signal has crossed it. So the meaning of this is the signal that has crossed the negative 10 dB, it is the signal radiating with minimum reflection. Those above negative 10 dB, they are reflecting back to the source. That's perfect. This is a perfect design. So let's check the frequency. So I'll bring a marker. I'll add a marker. Okay, so the marker is showing 4.3210 gigahertz. Okay, it's not exactly 4.3 because yeah, a lot of things, but it should be around the range, and this is around, so it's perfect. Okay, the next plot is going to be VSWR. VSWR is not plotted in anything, so you leave it like that. Okay, so as you can see, the 2, it has crossed the 2, so it's okay. The next thing that you do is you plot far field reports. You come to 3D polar plots. Okay, so you change it to sphere. You change it to sphere 1. So this TP. Okay, so this my 3D radiation pattern, which is having a maximum gain of 6.77. Okay, so okay, this one is red at the top here because patch antennas are directional antennas. Okay, so the gain is maximized at the tip over here. So the next thing you plot is your you come to far field radiation pattern, then you choose phi, then dB, then families. You come to here, select. Oh shit. Okay, so you select 0 and 90. Okay. Alright, so the phi the phi is over here. So you bring a marker on the marker to the top here. Okay, then you add another marker at the tip here. Okay, so the difference between this M1 and M2 magnitude, which is 6.7685 minus 6.8135, is called the front to back ratio. Again, let me plot the last graph and that's all. So far field radiation pattern I've done for phi. The next is theta. You choose dB, change to your sphere 1 that you've created. You come to families, you change it to 90 to 0 and 90, sorry. Then think you plot. Alright, so this is your H plane. So the smaller the shrinked object in the middle, the more effective the antenna is. Okay, so for this If you want to calculate for half power beam rate, you bring your marker. Okay, so the maximum gain is 6.77. You find a gain that is 3 dB less than this, which will be 3.77. You locate it. You look for it. As you are moving here, you check over here to see the magnitude. So moving, moving, moving. 6 point sounds okay. This okay. You not get exactly, but it's okay. Oh no, this is not it. So over here you stand at the center, you draw a curve. It's basically the same thing on this side. So is 1, 2, 3 should be on this. Okay. So the angle between these two marker M3 and M2, the angle becomes your half power beam width. So this tells us that if here is 30, 40, 50, so it will be 50 minus 50 is 100. So your half power beam width is 100 degrees, and that's your what's the name, half power beam width. Thank you. They save everything. Okay.